Dear students, welcome to Lion Rajmohan Sir's channel. In this channel, we have been sharing lecture videos for chemical engineering courses like chemical process calculations, mass transfer, biochemical engineering, fuel cells and batteries. Also, we have been sharing demonstration videos for the experiments in fluid and particle mechanics laboratory and chemical reaction engineering laboratory. In this video, we demonstrate experiment number 8 on chemical reaction engineering laboratory, which is reaction rate constant by dilatometry. To determine the overall rate constant and the catalytic rate constant for the decomposition of diacetone alcohol in aqueous solution catalyzed by sodium hydroxide at ambient temperature. Coming to the theory part of the experiment, we know that dilatometry refers to the method in which the changes in volume are observed and measured. The term dilate means to expand. So any determination of reaction rate constant would definitely require knowledge of the variation of concentration of reactants or products with time, and the variation of the concentration may be measured either directly by chemical analysis or indirectly by measuring certain physical properties. These physical properties may be pressure, volume, conductivity, which can be related easily to the concentration. In dilatometry concentration, changes are followed by measurement of volume of the reacting system. So in the current experiment, a homogeneous liquid phase catalytic reaction is studied. The kinetics of the homogeneous catalytic reaction is analogous to the kinetics of homogeneous non-catalytic reactions, except that the overall rate constant varies linearly with the concentration of the catalyst.
Apparatus required for dilatometry: 250 ml beaker, 10 ml measuring jar, glass rod and stopwatch, and this is dilatometry. Chemicals required for dilatometry: 0.1 normal NOH, 0.05 normal NOH and diacetone alcohol. In this we are taking 100 ml, 0.1 normal.
For the procedure of the experiment, we first need to measure 100 ml of the 0.1 normal alkali into a 250 ml beaker and add 5 ml of the diacetone alcohol by means of pipette. We now need to mix the contents well by means of a glass rod for about a minute. Once the mixing is done, we now need to pour the reacting mixture into the cup of the dilatometer, keeping the valve closed. After that, we carefully open the valve, allowing the reaction mixture into the bulb of the dilatometer, taking care that and seeing that no air bubbles are retained in the connecting U-tube or in the capillary of the dilatometer. If there is any air bubble, that will give us some error in the calculations. So then we need to adjust the liquid level in the capillary to some arbitrary value at the bottom of the scale. Then we close the stop clock and some excess liquid must be left over in the cup at this stage. We then note the reading of the liquid level and simultaneously start the stopwatch. We then continue noting the liquid level readings at intervals of half minute until the liquid level finally crosses the calibrated portion of the capillary. After this, the experiment is completed and we repeat the experiment using 0.05 normal alkali solution and using the same time interval of 1 minute. We standardize the alkali solutions using oxalic acid and note the room temperature. So now we are going to perform the experiment. For that, first we are going to measure 100 ml of 0.1 normal NaOH into 250 ml beaker. Is it? To it, now we are going to add 5 ml of diacetone alcohol. Now the contents are going to be mixed well by means of a glass rod for about 1 minute. After proper mixing is done, now we are going to pour the mixture into the cup of the dilatometer. After mixing it, we are now going to pour this mixture into the dilatometer, for which first we have to open the valve completely. The mixture is being poured on the left hand side of the dilatometer. Once the mixture reaches zero reading, we are going to close the valve completely. We also have to make sure that no air bubbles remain in the whole system. After closing the valve, we are now going to start the stop clock and then see for every 30 seconds the rise in the level. Once it reaches 30 seconds, we are going to stop the stop clock and then take the reading. The reading is 1.8. Thereafter, for every 30-second increment, we are going to note down the level of the reading. For 60 seconds, the level is 2.8. The next reading is 4. We note it down. The next reading is 4.7. We'll note that down. The next reading is 6.1. The next reading will be 7.2. Next reading is 8. Next reading is 9.1.
इस नीचे बबल है ऊपर वाले 10.2.
Next reading is 10.2. The next reading will be 11.2. We are using the compressor setup. For this, first we have to open the valve and then connect the pipe onto the dilatometer and ensure that no air bubbles remain in the dilatometer before we conduct the second part of the experiment. This is how we use it to remove the air bubbles. For the next step, now we are going to take 100 ml of 0.05 normal NaOH. We'll pour it into a beaker. To it, now we are going to add 5 ml of diacetone alcohol. After adding it, now we are going to stir the mixture for around 1 minute. Now, before pouring the mixture onto the dilatometer, we have to ensure that the valve is completely open position. We now pour the mixture into the left side of the dilatometer and allow the solution to settle. We are now going to take the solution until 0 reading and then close the valve completely. The level rises, now we have to close the valve at one position and then we have to start the stopwatch. As we can see here, the liquid level is rising. Once we start the stopwatch, we have to take the liquid level rise for every 60-second increment. As we can see here, the liquid level is rising in the capillary. It has crossed 1.5 for 30 seconds. Now in another 30 seconds, it will rise and we are going to note down that value. Once it has reached 1 minute, we are going to note down the value of the liquid level.
Yes, value.
It is 3.5. Now, again, we will allow the liquid level to slowly rise in the capillary and take the reading after 1 minute, that is 60 seconds. So you can see the level is rising. It has crossed 5.5 and slowly and steadily the liquid level is increasing. So at 120 seconds, we note down the value which is 5.7. 5.7, yes. We are now going to take the value at 3 minutes. We can see the liquid level is rising. So it has reached around 6.3. Yeah. So at 3 minutes, we get the value to be 6.5. We note this down. Similarly, we are going to take the other readings. So after again 60 seconds, we are going to take the reading. So at 4 minutes, we'll get the next reading. The liquid level is slowly rising. It is about to reach 7. So 4 minutes, we got the reading to be 7.2. We note this down. So using the stopwatch, now we are going to take the next reading at 5 minutes. At 4.30 seconds, the liquid level has risen to around 7.9. So at 5 minutes, we get the liquid level to be 8.1. So we need to note this value. So for the next reading, we have to take the liquid level at 6 minutes. At 5.30 seconds, the liquid level is around 8.6. So after 30 seconds, we have to note down the value so that we get the liquid level at 6 minutes. We got the value at 6 minutes to be 9. So we note this value. For the next reading, we have to allow the liquid level to rise for the next 1 minute. So at 7 minutes, we are going to get the next reading. We can see the liquid level is very slowly and steadily rising in the capillary. So it is slowly rising, and at 7 minutes we get the value to be 10. So now we will again allow the liquid level to rise in the capillary and check the reading at 8 minutes. We now move to the observation and calculation part for the experiment. In the observation and calculation part, first we need to standardize sodium hydroxide 0.05 normal sodium hydroxide and 0.1 normal sodium hydroxide using standard oxalic acid solution. Once that is done, we now need to take the dilatometric readings. So for different time in seconds, we will have the liquid level readings. So that will be denoted by Y and Y dash. So suppose there are 18 readings, then 9 should be taken as Y and the remaining 9 will be taken as Y dash. Once we note that down, so we can find out the ln Y dash minus Y values. Once ln Y dash minus Y and time is there, we need to plot a graph of ln Y dash minus Y versus T and report the modulus of the value of slope as k overall. So the slope that we get by plotting this graph will be the overall rate constant of the reaction. That will be reported in second inverse. Once we have the overall rate constant, we can find out the catalytic rate constant, which is nothing but the overall rate constant divided by the concentration. The concentration of sodium hydroxide at 0.05 normal as well as 0.1 normal. So we will have two dilatometric readings, 1 and 2. Once that is done, we complete the observation and the calculation part. Once the values have been calculated, we now need to report it in the results and discussion part. For that, we need to first report the values of the overall rate constant and the catalytic rate constant for both the readings. That is for 0.1 normal NaOH and 0.05 normal NaOH. Once these values have been found out, we need to discuss how the overall rate constant and the catalytic rate constant behaves with the change in the concentration. To plot the graph of ln Y dash minus Y versus time and find out the modulus through which we calculate the overall rate constant, we need these values. So these are some of the readings for practice which are needed for plotting
Classroom.
Finally, to summarize the experiment, we can summarize it in this way that the overall rate constant and the catalytic rate constant can be determined by plotting the graph of ln Y dash minus Y versus T, and for both 0.1 normal and 0.05 normal sodium hydroxide, where K overall will be the slope of that graph.